Good morning, everyone. Okay. My name is Gustavo Teles. I'm a senior researcher here in São Carlos, working with Vanderlei Banhato and others. And at this time, I will present you Professor Randall Hewlett. Okay. For those of you who don't know him, Dr. Hewlett, he studied at Stanford University. He earned his bachelor's degree in 1978. He then received his PhD in 1984, working at MIT under the supervision of Dr. Daniel Klappner. And then he joined the National Institute of Standards and Technology in Boulder with Professor Dave Wineland. Then in 1987, he became an assistant professor of physics at Rice University. And he was promoted to associate professor in 1992, okay, and then to a full professor in 1996. So he's on the road for a while now. And he pioneered experiments with ultracold and Bose-Einstein condensate. He's known for the first realization of Bose-Einstein condensation in atomic gas with attractive interactions, where the formation of a BEC competes with the usual condensation due to the two-body attractive interaction, causing the BEC to become unstable. And his group has measured that the system collapse, which was a very intriguing and interesting observation at the time. Another major achievement working with bosons was his realization of matter wave solitons, okay, in a BEC. He also performed pioneering experiments with the degenerate Fermi gases. He achieved his first observation of polarized degenerate Fermi gas, and realized the possible realization of FFLO state in 1D system a few years back, or actually a decade about or so back, in 1D system. His group has investigated fermions and optical lattices as model of systems of supersolid or solid-state physics, and observed short-range antiferromagnetism in a Hubbard system, similar to physics observed in cuprates high-temperature superconductors. He also received a number of awards over his career, including the Herbert Walter Prize in 2017 and the Willis Lamb Award for the Laser Science and Quantum Optics in 2011, and the I. Rabi Prize of the American Physical Society in 1995, and the Presidential Young Research Investigator Award at the National Science Foundation in 1989. So he's also fellow of the American Association for Advancement of Science in the American Physical Society. Hewlett is also an honorary doctor of the University of Utrecht, and so on. To finalize, he's a dear collaborator of a few groups in Brazil, including us, and he has been visiting Brazil for, I think, even late 1990s. He was already in Brazil in an Encontro Nacional de Física da Matéria Condensada. And he's a very dear friend and very flexible research, so you might enjoy. And here we go with his first talk of 3. Professor Hewlett, please.
Thanks, Gustavo. That was a very nice introduction. I appreciate it. It's great to be virtually back in Brazil. Unfortunately, I can't be there in person due to the circumstances, but I miss Brazil, and I hope you all are doing well. And I've enjoyed, as Gustavo said, many years of collaboration with Vanderlei and Gustavo and others in São Carlos and in São Paulo. So it's nice to be here. So I welcome questions during my talk, if that's allowed by the organizers. If not, I have no problem waiting till the end either. So however it works out. So I'm giving 3 lectures, 2 today and 1 tomorrow. And my first lecture is on BoseEinstein condensation, as Gustavo said. The second on an example of quantum simulation with ultra-cold atomic fermions, in which we saw magnetic correlations. And then thirdly, the fermions in one dimension is our most recent work. And it has to do that what I'll talk about is a manifestation of low dimensional physics, which is called spin charge separation. All right, so these are the people that have been involved in this work in matter wave solitons. Jason Wynn, Paul Dyke, and let me move my screen a little bit so I can see what I'm supposed to say. And graduate student Henry Luo at Rice. And we've had theoretical collaborations with Boris Malamed, Vladimir Yurovsky, and Maxim Olshani. And there is some really nice work that we did in collaboration with Vanderlei that I'm only going to briefly discuss, having to do with modulation of interactions. All right, so this is my outline of today's lecture, of this morning's lecture. I'm going to give an introduction to quantum gases and to solitons, to matter wave solitons, talk about soliton collisions and dynamics of soliton trains. If you don't know what solitons are, don't worry, I'll explain them in some detail. So let's begin by talking about quantum gases. So the quantum regime corresponds to a regime where the density is high enough and the temperature low enough that the density times the de Broglie wavelength cubed is of the order of 1 or greater. So this means that de Broglie wavelengths of adjacent atoms, say in a box like this one, begin to overlap. And when they begin to overlap, it matters whether the particles are bosons or fermions, and if there are identical particles. And these parameters that n lambda cubed be of order 1 is a requirement that, for example, the density of about 10 to the 12 per cubic centimeter, which is typical, which is very rarefied, I should add. This is a very low density. The molecules of air in your room is 10, at least it is in the United States, I assume it's the same in Brazil right now, has a density of about 10 to the 19 per cubic centimeter. So this is very rarefied gas, very low density, but the temperatures are correspondingly low, 100 nanokelvin. And that gives a de Broglie wavelength of about 1 micron. So when you achieve these quantum conditions, bosons will undergo a phase transition to a BoseEinstein condensate. That corresponds to, in our case, lithium-7. And fermions will can undergo a pairing transition to a superfluid state. So we work with lithium. Lithium-7 is a composite boson because it consists of an even number of spin-and-a-half particles. So if we look at the number of electrons, protons, and neutrons, then we see as a composite, it has 10 spin-and-a-half particles. And because that's an even number, that corresponds to a composite boson. And in the case of lithium, about 94% of the natural abundance of lithium is the bosonic lithium. And at T equals 0, everything condenses into this lowest ground state level of whatever is confining it. So a box, a harmonic trap, or what have you. And for lithium-6, which has just one fewer neutron in its nucleus, that now has a odd number of spin-and-a-half constituents. And so it's a fermion. It's a half integer spin particle. And fermions behave very differently than bosons. So this is kind of an interesting realization that even though lithium-7 and lithium-6 are chemically identical, because of their statistics, they're actually very different at low temperatures. In the case of the fermion, if we have it in a box or harmonic well, as illustrated here, there'll be one particle per state up to an energy that we call the Fermi energy. This is the highest occupied level. So that you can see is very different than over here. All right, so let's move on. So these are some of the things that people have been able to study with bosonic atoms. They've made vortices and solitons, as I'll describe, atom lasers, the Josephson effect. I think you're going to be seeing a talk by Giacomo Roati from Firenze, and people have seen Mott insulator transitions, which is a many-body effect, and also few-body effects, F of molecules, one-dimensional physics, as I'll describe later tomorrow, disorder, etc. So there's a variety of things that people have studied, many now which fit into the description of a quantum simulation, the many-body simulation of some Hamiltonian that may describe electron physics, for example. So with many-body physics, there are very many examples of quantum simulation that have been recently realized or not so long ago, pretty recently. And people are studying quantum magnetism, and I'll describe our experiment along those lines later this morning. This morning for me, I guess not for you. Exotic superconductivity, as Gustavo mentioned, we're studying something called FFLO physics. Strongly interacting one-dimensional systems, and that'll be the focus of my third lecture tomorrow. Quantum criticality, disordered insulators, etc. Topological matter, most recently. And many of these things are realized by using optical lattices. So if you look at a potential which is produced by a standing wave of light, you can make an array of two-dimensional pancakes along one axis. Now, if you make an optical lattice with two standing waves, in this case, square geometry, you can realize a square array of one-dimensional tubes. And this is exactly what we do in our one-dimensional physics experiment that I'll describe tomorrow. And then finally, a three-dimensional optical lattice, in this case, a simple cubic optical lattice, can be constructed with three standing waves. More complicated geometries, triangular lattices, hexagonal lattices, etc., can also be realized using light, simply because by retro-reflecting beams, the beams interfere and produce a periodic potential that the atoms experience. And all of these experiments that I've described over here on the right have relied on the ability to tune parameters in a very controlled, nice way. So in particular interactions, and I'll talk a little bit about Feshbach resonances and how interactions are tuned by Feshbach resonances. But also you can adjust things like hopping or tunneling between one site and another site on an optical lattice. You can adjust temperature, density, as I mentioned, dimensionality, geometry, spin polarization, spin orbit interaction, et cetera, et cetera, et cetera. It's really, truly amazing, the flexibility of these systems. Okay, so that brings me to a description of interactions in these gases. And the interactions are dominated by two-body interactions because the densities are so small, and we're dealing with single atoms that that are, well separated by a border of a micron, which is, or to enter this quantum regime, the magnitude of the de Broglie wavelength. And that's long compared to a typical van der Waals interaction of, say, a nanometer between two atoms, two, let's say, alkali metal atoms that are single electron valence atoms. And because of this ratio of 1 micron to 1 nanometer, it means the detailed shape of this potential is not important. And we can describe this interaction by a single parameter. Could be the S-wave phase shift or the S-wave scattering length that is denoted by this symbol A. So the mean field interaction energy is let me move this thing. The S-wave interaction energy is governed by a mean field, and the mean field, the magnitude of the mean field is proportional to density times this parameter, the scattering length. And you can see if the scattering length is positive, that corresponds to a positive potential, positive mean field. And if A is negative, it corresponds to an attractive one. And I'll describe now some of the implications of these attractive interactions. So in 3 dimensions, the mean field interaction energy, which is proportional to A, and attractive interactions corresponds to a negative A, the condensate's mechanically unstable, and there's no BEC in free space because it would rather collapse into high density little black hole if that were the only interactions, other than, there is a hard core that keeps the atoms apart when they get very, very close together. But this mean field interaction energy is negative for attractive interactions, and there's no BEC in free space. However, this is very important, and it took us a while to realize this, is that the atom condensate is stabilized by quantum pressure when they're confined in a trap. So they have some finite size. So you know that if you take a harmonic oscillator potential and you look at the energy levels of that potential, that they depend on the strength of this omega that describes the harmonic well. And as you make omega bigger, the energy level splitting increases. And so you can see that because of this effect, of this quantum uncertainty effect, that squeezing to higher density, to smaller confinement, the condensate resists doing that because of this 0-point energy. And the force of attraction due to the mean field interactions can be balanced by this so-called 0-point energy, the energy of the ground state, which is proportional to the frequency of this harmonic oscillator. So up to a point, you can have a condensate which is stable, beyond that point, it undergoes a catastrophic collapse into a little bosonova. So BEC is possible with negative A, but the condensate number is limited. And it turns out that condensate number is limited by the size of the confinement, as you might imagine. This is the harmonic oscillator scale length, divided by the magnitude of A, and that gives a critical number. And the critical number in our geometry is, typically of order 1,000 or so. So this is what it looks like. This is experimental results from a long time ago now, a couple of decades ago. This is showing a direct image, unprocessed image of atoms in situ in a harmonic trap. So this is what the density profile looks like. there's a broad pedestal, which is green and yellow in this image, and then a little peak that sticks out of it. And that little peak that sticks out is the BoseEinstein condensate. And if you keep adding atoms to this condensate by quench cooling it so that it fills up to this critical number of about 1,000, you go beyond that and it collapses. And so that little peak disappears into this cloud of thermal atoms. And if you quench it some more, cool it, it'll begin to fill again and undergo this cycle of collapses followed by refilling, followed by collapse, followed by a reestablishment of the condensate. So this goes on as long as you have atoms that can fill this condensate up. So that we saw in about 2000. And also at Gilla in Carl Wyman's group saw a similar effect. So we call that the bosonova. This was a prosaic term that was coined by Eric Cornell to describe this explosion process of this BoseEinstein condensate. All right, so how do we tune interactions? So we've seen the interactions are determined by the S-wave phase shift or the S-wave scattering length. And so it's just kind of luck of the draw. It's kind of depending on what that phase shift is. The potential is a little bit deeper, a little bit shallower. You can change the sign of the scattering length and certainly change the magnitude of the scattering length quite readily. If you could change the potential phase shift in some way, change this shape and depth of this van der Waals interaction between two atoms. Well, it turns out you can by a magnetic field. And the reason that you can is that these atoms, if they're in the same